All right, ladies and gentlemen, today we're going to be talking about the ideal gas law. As you can probably guess from the gas law name there, this is used when a gas behaves in a perfect or ideal manner. So this is going to relate amount, pressure, volume, and temperature, everything that we talked about so far. So this is how we're going to derive it. We're going to use our combined gas law. So P1 V1 over T1 equals to P2 V2 over T2. Now for a specific gas, we know that pressure times volume divided by temperature is equal to some constant. That's how we can get from step one to step two, from the before and after, is we know that that is equal to some constant. It doesn't change. So we also know that its amount is directly proportional to volume and temperature. So if you add more, the volume and temperature, or the volume and pressure, are going to have to go up to compensate to keep that at the same constant. So we represent that with a little n on the bottom there. So n, as we're going to talk about on the next slide, is going to be equal to number of moles. So we have R represented as the ideal gas constant. So that's that constant, that some constant at the bottom, representing with I for an ideal gas. We call it the ideal gas constant. So we have PV over NT equals R. So what those are, and I rearrange the equation there just to get it in the most standard form. So we get NT from the bottom to the top on the opposite side. We get PV equals nRT. All right, so P equals pressure, V equals volume in liters, N is the number of moles, so moles. T is the temperature in Kelvin. Now pressure, we have a bunch of different pressure units that we've talked about in here. We're going to choose our R volume, or R value, based on the units of pressure. So you can see all of these units on the right-hand column have liters per mole Kelvin on all three of them. Liters per mole Kelvin, liters per mole Kelvin. The only thing different about them is atmospheres, kilopascals, and millimeters mercury. What those are is because of the pressure that we choose. So whatever our pressure is in, we choose an R value that correlates with that, so we don't have to use all those conversion factors. So write these three down in your notes with those units. Make sure you have those so you can look back at them. All right, first example we're going to do together. Find the temperature of a gas if 0.387 moles of it have a volume of 1.921 liters and exert a pressure of 1.01 atmospheres. So we're going to write down what we have. So we have P, V, N, R, and T. Those are going to be our variables from this problem. So we can pull those straight out of the problem. So pressure is 1.015 atmospheres, volume is 1.921 liters, and our number of moles is 0.387 moles. So how do we choose what R is in this case? So we look back at that chart that we had. We find the one that has atmospheres because we have atmospheres given to us in the problem. So we have 0.0821 liter atmospheres per mole Kelvin. So we have that atmospheres and the atmospheres that match up, so that when we plug them in, those will cancel out. We don't know our temperature, that's what we're looking for. Set up our equation, PV equals nRT. I'm going to rearrange it because we want temperature to be alone on top. So to get temperature alone, we divide by N and R because those are multiplied by it over here. So divide by them, cancels them out, moves them to the other side. We can rearrange our equation, put T on the left side equals PV over NR. Now I'll plug in for temperature, get those values from our problem, solve, we get 61.4 Kelvin. You can leave this in Kelvin, you can convert it to Celsius. If I ask you for specific, make sure you put it in that. So next thing we're going to talk about is the molar mass relationship. So molar mass is equal to grams per mole. Mass, M is G, N is the number of moles. So we have our equation over here. So the number of moles is equal to the mass divided by the molar mass. So N is in our equation that we have, so we can substitute. So we have PV equals nRT. We can throw that M over mass over molar mass into our equation. So we get PV equals mRT over capital M. Rearranging for our equation to get molar mass alone. We get molar mass is equal to mass times the ideal gas constant times the temperature divided by the pressure times the volume. Now, density relationships as well. So density, we already know, is grams per liter. So we have mass in grams, volume in liters. Density is equal to mass over volume. So we had mass in that relationship that we just found. So we have the molar mass is equal to mass times R times temperature divided by pressure and volume. We can substitute in that mass. So we rearrange our equation. We get D over V. So we can put that in there. The V's will cancel out. And then we get our rearranging for density. We get density equals molar mass times pressure divided by the gas constant times temperature. So we'll do a couple problems with this in class. So write this down in your notes. We'll get this together. Find the pressure in kilopascals of nitrogen gas if its density is 0.863 grams per liter and it's held at a temperature of 20.1 degrees Celsius. Write this one down as well. So how many moles of gas are in a sample with a temperature of 18.21 degrees Celsius, a pressure of 745 millimeters mercury, and a volume of 3.517 liters. We'll do those together. You guys will do these next two with a partner. So what volume of oxygen gas is a mass of 1.342 grams, temperature of 226.2 Kelvin, and a pressure of 0.935 atmospheres? And then also write this one down. What temperature is 231.4 moles of gas? What temperature is 231.4 moles of gas at 101.3 kilopascals if it is in a container that is 5.125 liters? Write those down, get those ready. We'll go over those in class. Look forward to seeing you.